Hello everyone. Hello. Welcome you all to the problem solving session. Okay, it is 7 minutes past 6. I will do it for another 3 minutes and then I will start the problem solving session. Hi, Tejaswini Thirumurthy. Am I spelling it properly? Um, you can hear me. You can just raise your hand or just answer. It would be really helpful for me. So, am I audible? Hello, Bharat. Hello, Tejaswini. Welcome. Um, Bharat, can you mute yourself? Uh, yeah, thank you. Thanks. So you can hear me, right? Just a confirmation from your side, like it would be really helpful for me. Okay, it's almost 10 minutes past 6. We'll wait for another 2 minutes and then we will start this problem solving session. Okay. I guess it's fine with you guys. So inform me if my voice is breaking or screen is not visible, because there will be no other way for me to confirm it. Okay, so a little bit cooperation from your side would be really appreciated. I think as of now I'm audible, right? Bharat? Okay, let us start the session. Is the screen visible to you all? Just confirm once so that I can proceed. Anyone? Okay, let us start. So, welcome you all to the problem solving session of the NPTEL course titled Multirate DSP. This is our first discussion, week 1. So, let me introduce myself. I am Saurashis Chatterjee, a PhD scholar at IIT Kanpur, and today I'll be holding this problem solving session for you. So let us quickly move to the first problem. So here the first problem, as you can see, says continuous time signal cos 100 pi t is sampled with a sampling frequency of 200 hertz to obtain a discrete time signal xn. So what is the resulting signal xn going to be? So guys, this is a basic digital signal processing question. Okay, before we start, I just want to inform you all that this is supposed to be an interactive session, so I'll be really happy if you guys participate. So anyone willing to answer how we can proceed to solve this problem? Just maybe a little step. Okay, let me start. So your continuous time signal xt is given as cos 100 pi t. You are going to sample this signal with a sampling frequency fs is equal to 200 hertz. So that means your sampling time TS is basically 1 over 200 second, of course, because the formula is given as 1 over Fs. So the procedure to obtain xn is basically you are taking this continuous time signal and sampling it at instance t is equal to nts. So just replace t with nts in the expression of xt and you will get the discrete time signal, which is given as cos 100 pi nts. Let me put the values of ts. It's like 100 pi n times 1 over 200. So it turns out to be cos pi n over 2. So as you can see, the third option is the correct one. You guys have any questions regarding that, or should I move to the next problem? You can ask freely, like any doubt, and you can also stop me at any point of time while solving this. So there is one thing I want to mention here. You see this cos 100 pi t, when we say the basically the frequency of the signal is 50 hertz. You can see basically the analog frequency omega is given as 100 pi, which is basically 2 pi times f. F is the frequency content, so it turns out to be f is equal to 50 hertz, and you are sampling it at 200 hertz. So according to this Nyquist criteria, when you are supposed to sample a signal at least twice the maximum frequency component, so the frequency component of xt is 50 hertz. Therefore your Nyquist rate is Fn is 2 times 50, 100 hertz. So when you are sampling at a frequency of 200 hertz, you are basically over satisfying the Nyquist rate, which is good. Why? We will come to that at a later point of time when encountering a problem which is mentioned later. So let us move to question number 2. So Bharat, you are willing to volunteer for this question, like how we can approach this problem to solve in a elaborate way, of course. Okay, fine, let me give you the answer. Here xt is given as cos 300 pi t times sine 400 pi t. So it's a we are going to use a trigonometric formula like this one, bracket sine A cos B is equal to half sin A plus B minus cos sin A minus B. Am I correct with that? Okay, fine. Therefore xt comes out to be sine of 700 pi t minus sine of 100 pi t. So you see there are actually xt constitute of two different frequency signal, where frequency of this part I denote it as f1 is 350 Hz. How I am reaching it? Again, the analog frequency omega 1 is 700 pi. That means basically it's 2 pi times 350. So your f1 is 350 Hz. At the same time, this second signal component has a frequency component f2, which is given as 50 Hz. So the question asks what is the Nyquist rate for this combined signal, which has two different frequency components, 350 Hz and 50 Hz. Now here you have to proceed very carefully, because you see what is the Nyquist rate. Nyquist rate is basically twice the maximum frequency component of the signal. Let me write it down somewhere here. Nyquist rate. Nyquist rate. It basically say that is equivalent to twice the maximum frequency content of the signal. So xc t constitute of two signals. One have a frequency 350 Hz, another one has frequency 50 Hz. So the Nyquist rate is Fn is going to be 2 times max of 350 comma 50, whichever is maximum. So in this case it is come out to be 700 Hz. Sorry, this Hz things will not be there. It's a dimensionless quantity, so the answer is going to be 700. Now if you are having Anaga, can you please unmute mute yourself? Yeah, thanks. So my screen is still visible, right? Whatever I am writing, can you just confirm once? A response from your side would be really helpful, guys, because I have no way to figure out whether the voice is breaking or this. You can see all these things. You can raise your hands also once to just confirm or write something that you are able to hear me properly and whatever I am writing. uh, I'll really appreciate that. Bharat, Anaga, anyone? Okay, okay, okay. Thank you, thank you, thank you, really. I missed it. Sorry, sorry. I have not seen the message earlier. Sorry. And no need to address me as sir. Just call me by my name, Sorasis. It's more than enough. It's fine. Sir is like really embarrassing for me. Okay, let us move to the presentation. So we got the Nyquist rate of the signal xt as 700. I want to warn you of one thing we often miss, that twice this maximum part we often miss. So you see, a part of this signal xt is given as sine 100 pi t, and you get the frequency f2 50 hertz, and you complete, sorry, just a moment, and you completely ignore this part. You take this one as the frequency component of the signal, and you take the 2 times of 350, that is 100, and you write the answer as 100, but which is not correct. In when the definition of Nyquist rate, this maximum part really plays a role. No matter how many frequency components your xt contains, you should always consider the maximum frequency while considering the Nyquist rate. The 2 times the maximum frequency is going to be your Nyquist rate, no matter how many frequency component your signal possesses. So that's a really important thing. So let us move to the third question, which is given as, let me write it down, xt is equal to 5 plus sine 50 pi t plus cos 150 pi t. So the concept is really similar to the previous question, just this constant part is introduced to kind of confuse you. Let me tell you, this is a constant, which means it has zero frequency. In other terms, you can also call it a DC signal. You can also write it somewhat like that, that cos 0 of t. Basically, it has zero frequency component. So while considering the Nyquist rate, what really matters are these two parts. So sine 50 pi t, the analog frequency omega 1 for this signal I take, so it is 50 pi. The corresponding frequency f1 is therefore 25, because it is given as, just as I discussed in previous slides also, omega 1 over 2 pi. For this signal cos 150 pi t, similarly we note the analog frequency. By the way, I am saying analog, this is a analog signal, is 150 pi, and we write f2, the frequency component. Sorry, it has to be mentioned in hertz, and this is radian per second. These are really important for understanding purpose, and this is 75 Hertz. Okay, so again similarly, when we are considering the Nyquist rate, here I am going to denote it as f r. It's twice the maximum of f1 comma f2, that is 2 times max of 25 and 75. Of course it is 2 times 75, the answer is 150. So 2 is really the answer for this. By the way, whenever you encounter any constant part, basically consider that as a DC signal which has zero frequency component. So while computing Nyquist rate, there may be as many as DC component, but that doesn't really matter. So sometimes this question arises to confuse you. Just remember it. Okay, so in this question the similar thing only, but it becomes little bit tricky when xt is given as 9 sine cube 500 pi t. So you have to use the trigonometric identity like sine cube. We cannot really find Nyquist rate that way. We can need to write it in terms of sine only. So anyone willing to volunteer how we can write it? Anyone like Anaga, Bharat? Like, we are going to use a trigonometric identity, of course, but what is that? Okay, let me write it. Basically the formula, um, remember, it is sine cube x is given as 4 sine x, sorry, 3 sine x minus sine 3x divided by it is 4, as far as I remember. If any of guys remember it, just correct me if I am wrong. As far as I can remember, it is 3 sine x minus sine 3x over 4. So if I am willing to write that here, it's 9 times. So basically this constant doesn't matter, but since it is given in question, we'll consider it. 3 sine 500 pi t minus sine 1500 pi t over 4. So I am ignoring this 9 over 4 part, so I am writing this as just proportional to, I am willing to consider only the frequency component, that is sine 500 pi t minus sine 1500 pi t. So again you see xt has two frequency components. The analog frequency corresponding to this part is given as 500 pi radian per second, and the corresponding frequency in hertz we can write as 250 hertz. Similarly, for this frequency component, continue analog frequency in radian per second is given as 1500 pi radian per second, and corresponding f2 is given as 750 hertz. So like previous two problems, Nyquist rate, if we denote as f of n, it is 2 times max of f1 comma f2, which is 2 times max of 250 comma 750. That is, you choose the maximum of them, 2 times 750, you got 1500. So your answer is basically this one. By the way, if you guys have any kind of queries, just stop me and ask, because even if you write something, I won't be really able to see because my screen now in the slideshow mode. So yeah. Okay, let me check if you have written anything or asked. Okay. Okay, nothing is there. Fine, fine. Okay, here comes a problem which says x c t is equal to sine 30 pi t plus cos 60 pi t, and you sample it with a sampling period t, continuous time signal you sample with a sampling period t, and get a discrete time signal denoted as xn, which is given as sine pi n by 3 plus cos 2 pi n by 3. Okay, so based on the previous solutions, can any of you tell me how to find the value of t? Any idea? Maybe just a first step. Come on guys, like just whatever it is, whatever is coming to your mind, like how we should proceed. This continuous time signal xt is sampled with a sampling period t, we get a discrete time signal, very fine. We need to find this t, which is consistent with the sampling process. So how can we proceed? Okay, I guess you have written something. Let me check. Okay, Bharat says question number 5 is not visible. Uh, okay, just a moment. Bharat, can you see it now?
Yes, sir.
Okay, okay, okay. Thanks, really thank you. So, any idea how we can proceed to solve this problem? Like you can just say it out, whatever it is. Maybe it's like weird or something, but no problem, fine. Okay, let me take the basic conventional approach how to do that. So we make use of this understanding that we sample like let's say that the sampling time is ts, and we are going to sample, like we are going to sample xct at ts point, then 2ts, then 3ts, like that, basically at nts when n is integer. Okay, so how can I get xn? Xn is basically nothing but, as I have shown in the previous slide, xct sampled at instant t when t is equal to nts. ts is the sampling time, n is the integer. When you are going to sample this continuous time signal xct at t is equal to nts, you are just going to get xn. So let us see how it goes on. So it's like sine 30 pi nts plus cos 60 pi nts. Okay, fine. So let me just compare, let me write these things also. These things I'm writing here for your understanding purpose, that the question says xn, sorry, xn is given as sine pi n by 3 plus cos 2 pi n by 3. So let us compare these two. Like, okay, forget about this cos term, let us compare these two. This sine 30 pi nts and sine pi n by 3, they should be equal. So let's make them equal. 30 pi nts is equal to pi n by 3. We can see both side has pi, so we can remove pi. I have n both sides, so we can also cancel n. So we are left with ts. I am bringing 30 to here. ts becomes 1 over 3 times 30, which we can also write as 1 over 90. Fine. So our sampling period ts comes out to be 1 over 90 second. So we can see that this is a answer, but we cannot stop here. See the options, there are 3 options, and there are another option that says that 1 or 2 may be the answer. So we already know that 1 over 90 is the answer, correct? But we do not know whether it is the answer or not. So if we mark this as correct, and if somehow this also comes out to be a possible ts, then actually this 4 should be correct and you are doing wrong. So you have to verify for other values of ts whether they are satisfying the same condition or not. So when we compare these two here, we are basically comparing sine 30 pi n ts with sine pi n by 3, correct? But you can see we can also write sine pi n by 3 plus 2 pi n, that is n is a integer. So when n is a integer and sine anything with a, it's periodic with 2 pi, so sine pi n by 3 plus 2 pi n is equal to sine pi n by 3. We can write this because this is periodic with period 2 pi, correct? So this thing can also be written as sine pi n by 3 plus 2 pi n. Okay, if you add these two up, just a summation, you see it is 3 over pi n plus 6 pi n, that is basically sine of 7 pi n by 3. Just remember this thing, this sine 30 pi n ts is also equal to not sine 7 pi n by 3, not only equal to sine pi n by 3, but it is also equal to sine 7 pi n by 3. Let me introduce one slide here so that we can continue the calculation. Okay, just a moment. So remember this result, that sine 30 pi nts is equal to sine 7 pi n by 3 also. We are going to use this. So we have seen that sine 30 pi nts is equal to sine 7 pi n over 3. So from this equation we can write 30 pi n ts is equal to 7 pi n by 3. Like before, you can see n is common, so we can remove them. Pi is common, we are removing them. We are moving this 30 here, so we get the value of ts as 7 over 90. So earlier we got ts is equal to 1 over 90. Actually both answers are correct. So see the question that it asks, which of the following value of t are consistent with the sampling process. So we have shown mathematically that both 1 over 90 and 7 over 90 are correct. If we sample this signal xt, whether with 7 over 90 or 1 over 90, we are going to get the same discrete time signal. Let me write it down for you for clear understanding. If we sample the continuous time signal xct given by sine 30 pi t plus cos 60 pi t with sampling time tsms denoting at ts1 is equal to 1 over 90 and ts2 is equal to 7 over 90 in both the cases we are going to get same discrete time signal x n given by sine pi n by 3 plus cos 2 pi n by 3, and there is a reason because of this happening. It basically happens because of aliasing, and I will discuss aliasing with you with reference to this question if we have more time after we solve the other problems. Okay, so remember that the same continuous time signal, if you are sampling at two different sampling at two different sampling time, like so to for basically sampling time is alternative way to say sampling frequency also. Basically, if you going to sample a continuous time signal with two different frequency, you can end up with the same discrete time signal, and this will happen because of aliasing. Okay, let us move to the question 6. It says, see, the signal xct means continuous time signal is passed through a continuous to discrete time converter, a CD converter, and the obtained discrete signal xn is passed through an ideal low pass filter with cutoff frequency pi by 4 radians per second. If xc is band limited to 5 kHz, what is the maximum value of sampling duration Ts that will preserve all frequency components from low pass filtering? So there are a lot of information in this question. Let us go through the question again. Basically, you are passing a continuous time signal through a continuous CD converter and you are obtaining a discrete signal xn, which is fine. You are passing xct through a box which performs this CD conversion. At output, you are going to get this discrete time signal xn. This passed through a low pass filter with cutoff frequency pi by 4 radian. You obtain this xn and you are passing this xn through a low pass filter with cutoff frequency pi by 4 radian, and you want to preserve all the frequency components. You receive some signal here and you know that your signal xt is band limited to 5 kHz. That basically means if we draw the spectrum of xc, which is denoted as, we denote xc of j omega. It is band limited at 5 kilohertz. So the spectrum of continuous time signal xt will look something like that. The scale is in kilohertz. So its maximum frequency component is 5 kilohertz, or it is band limited to 5 kilohertz. So you want to find the sampling frequency at which you perform the sampling here, or sampling duration. Both can be used interchangeably, which preserve the all frequency components from low pass filtering. What it means that we want this this complete spectrum, correct? We do not want something like let me mention with a different color. We don't want something like this. This is something we do not want. We want this entire spectrum unchanged. We want this complete spectrum. So at what rate, or at what frequency, or what should be my sampling duration, so that the resultant discrete signal, when passed through this low pass filter with this cutoff frequency pi over 4, will preserve all frequency components. So to solve this question, I think it is better for you to understand things in the frequency domain. So first of all, let me write down the frequency response of low pass filter, whose cutoff frequency is given over omega c is pi by 4. Omega c is the cutoff frequency. See, in discrete domain, okay, I guess some of you has asked some question. Let me check once. Okay, no one has asked question, it's fine. Okay, so your discrete domain, when you say that your low pass filter has a cutoff frequency pi by 4, so it is represented as something like that. By the way, discrete domain, your maximum frequency content can go up to pi. 2 pi is the maximum limit, so your maximum frequency is going up to pi. So in discrete domain, you are going, your low pass filter, the frequency response is going to look something like that. So you can see, if low pass filter is going to remove all the frequency component of xn which falls outside this pi by 4 range. Okay, so let me write it down. Low pass filter is going to remove all frequency contents of xn outside this frequency region minus pi by 4 to pi by 4. So this is another way of saying you have to sample at such a rate Ts such that the spectrum of xn is going to limit itself by pi by 4. What I mean by that, I am coming to that point. So my spectrum xn, spectrum of xn in discrete frequency domain should be at max can be like that. Sorry, not minus here, only pi by 4 to minus pi by 4. This should be the spectrum of xn in the discrete frequency domain, in the frequency domain, because if spectrum of xn crosses this limit of pi by 4, this low pass filter is going to remove that component. So your spectrum of xn can only stay between minus pi by 4 to pi by 4. So let me introduce a new slide. So as we are discussing spectrum of xn at max need to stay in the region minus pi by 4 to pi by 4. Minus pi by 4 to pi by 4. Now this is the spectrum of xt in the frequency domain, which is 5 kilohertz. Okay, now when we sample it at a when we sample xct at a frequency 1 over ts, we create multiple spectrums of xct, something like that we create. Minus 5 to 5, consider this is your fs, that is ts is the sample duration, 1 over ts is your frequency at which you are sampling. It creates multiple copies. Now if you move the spectrum in the discrete frequency domain, this 1 over ts translates to, let me write it here, 1 over ts, which is nothing but fs, translate to 2 pi, and rest of these things. So if it becomes 2 pi, you can see this. Okay, if it becomes like my spectrum is 2 pi here, this is the maximum frequency of the signal it can take, minus pi. Here it is minus 2 pi, something like that. So to avoid aliasing, I just need to do okay, I think I made a mistake here, sorry about that. Need to correct it, sorry, really sorry. Okay, fine. Okay, let me correct myself. Okay, so spectrum of xn should be something like this, as it is mentioned here. It is at 2 pi, somewhere here it is minus 2 pi. So this 2 pi corresponds to 1 over Ts. Now my spectrum of xn cannot go beyond this minus pi by 4 to pi by 4, because otherwise we have seen the, let me draw the low pass filter on top of that so it would make it clear. So my low pass filter is something like that. Yes, sorry for the drawing. This is my low pass filter. It stops at pi by 4. It is going to remove any component that goes beyond pi by 4. So xn can, if xn I am willing to recover all the frequency component without distortion, my xn at least should stay between this low pass filter cutoff frequency, that is its maximum component frequency component can be allowed to max to pi by 4, where we have these copies of this spectrum at 2 pi in discrete frequency domain, which continuous time you can translate to 1 over Ts or Fs. So if 1 over Ts corresponds to 2 pi, then pi by 4, the maximum frequency component of x is, we see that it is 5, sorry, yeah, so maximum frequency component of xct we have seen it is 5 kilohertz, which corresponds to pi by 4. Therefore 2 pi corresponds to 40 kilohertz. So 1 over Ts is supposed to be 40 kilohertz, or my sampling rate Fs should be 40 kilohertz. That means we can in other words say that Ts is 1 over 40,000. I messed up here somewhere, so let me clear the things once from the beginning. So this is the design of low pass filter, which is not going to allow any frequency in this shaded region. It will only allow the frequencies inside this box, that is from minus pi by 4 to pi by 4, and going to cut off all other frequency components. Now XC has a maximum frequency component of 5 kilohertz. That's another way of saying that XT is band limited to 5 kilohertz. Now when you sample XC at with any sampling rate, you create this kind of multiple spectrum, multiple copies of XCT, which are spaced at which are periodic with 2 pi, and yeah, that is it. So your spectrum of this sampled signal xn at most can stay between minus pi by 4 to pi by 4 if it is willing to protect all the frequency components, because the moment it goes beyond pi by 4, the low pass filter, which is denoted as this blue rectangular box in this image, is going to cut off the frequency component. So whatever the sampling rate, the spectrum of xn should stay between minus pi by 4 to pi by 4. Now the 2 pi here corresponds to 1 over ts, the sampling frequency. Therefore if I am willing to protect my frequency component of 5 kilohertz, it should coincide with this pi by 4 in discrete frequency domain, should coincide with 5 kilohertz. From this relation we can get 2 pi corresponds to 40 kilohertz. That is, we need to sample at a rate of 40 kilohertz to preserve all the frequency components of the sampled signal when it is passed through this low pass filter, which has a cutoff frequency pi by 4. Therefore we get the sampling period or sampling duration, whatever you say, as 1 over 40,000, which is the option number 4. If you are having any problem in understanding, you can stop me at any moment. I somewhat make the explanation a little messy for this question, not a little, a lot messy. So if any of you is having a problem in understanding, you can ask me. I will try my best to clarify things. I am assuming that things are fine. Okay, then I am moving to the next problem. Okay, that is a extension of the previous problem. It says, okay, we need to go in a little bit different direction this time. It says that this time the sampling frequency is 20 kilohertz. That is, if you write the sampling frequency fs in terms of the sampling duration or sampling period ts, it is 20 kilohertz. Fine. It says that what should be the local cutoff frequency of low pass filter that preserve all frequency components. Fine. Okay, this gives me a chance to explain the problem again. So let me draw the spectrum of xct, which is denoted as xcj omega. It is like, you can write it 10 pi also in analog frequency, or in terms, 10 to the power cube in terms of analog frequency, or in terms of only frequency you can just write it as 5 into 10 to the power 3. 5 into 10 to the power 3. I'm just writing it as 5 where I consider the scales is in kilohertz. So when you are going to sample it at a sampling period of Ts, you are going to create multiple copies of the same spectrum of the same thing. Okay, you are going to create copies like that. Whatever be your sampling period, if it is given as Fs, then it is periodic with Fs, it is 5. When we translate the whole thing, the axis from in digital frequency or discrete frequency, this corresponds to 2 pi. Okay, let us it in question already given that Fs is 20. Fs is 20. Therefore, if according to this picture, if 20 corresponds to 2 pi, your maximum frequency component at this point, sorry, consider it is 5. So 5 should corresponds to pi by 2. So in discrete frequency domain we can represent the same spectrum as this, like this. It is again multiple copies which is periodic with 2 pi minus 2 pi, and this is pi by 2. For example, this is 3 pi by 2, this is minus pi by 2, and so on. So this is the spectrum of Xn. Now if I design a low pass filter, suppose I am designing a low pass filter which is denoted in blue ink like this, sorry for the messy drawing, like this, which goes from minus pi by 2 to pi by 2. That is, this low pass filter is going to allow all frequency components below pi by 2 and going to cut off rest of them. So if I design a low pass filter which has a cutoff frequency, which let me denote as omega c is equal to pi by 2, it is not removing any frequency component of Xn. See, it is not removing any frequency component of XCT, it is preserving all the frequency components. So the local cutoff frequency of low pass filter that preserve all frequency component, the answer should be pi by 2. And remember, it keeps changing with the sampling frequency. Here if the sampling frequency changes, then to preserve all the frequency component, then the spectrum shape will remain same, but it may get stretched or squeezed based on this sampling frequency, and based on that your cutoff frequency of low pass filter can be very different for this case. So the local cutoff frequency or the cutoff frequency of low pass filter is very much dependent on the sampling rate, remember it. Let us move to the next question. Okay, which of the following operation are non-causal? So first of all, let us understand what is causal. I won't go to the theoretical definition as of now because you can find it anywhere. Let's try to understand from an example. Basically, causality means your function value is 0 for t less than 0 in case of continuous time signal, or for discrete time signal n less than 0. Causal systems are those systems whose output at present time only depends on input at present and or past time instants. This is causal. Therefore, non-causal systems output depends only on input at future time instants. So let me consider the function unit step function ut, which is basically takes value 1 when t greater than equal to 0 and 0 when uh, t is less than 0. So if I am asked to plot this ut, it's like something of this sort, something in the red color. For all values of t which is less than 0, for all values of t which is less than 0, that is negative, ut is 0, and for t greater than equal to 0, its value is 1. Fine. So we need to find which of the following operations are non-causal. So we are going to apply operation over this function one by one and see what the outcomes is. Now delay operation is something when you have a function xt, delay operation results into xt minus tau, where tau greater than equal to 0. So let us consider the delay operation on ut when tau is equal to some positive value, let's say 3. So let's consider the effect of function values of ut minus 3. According to the definition of unit step function, it is going to be 1 for t minus 3 greater than equal to 0 and 0 for t minus 3 less than 0. This is nothing but 1 for t greater than equal to 3 and 0 for t less than 3. If we are to plot it, it is something of this sort. So you see, for negative values of t, the function value still remains 0. So basically, when you are delaying a function, the delay operation causes shift on the right side of the time axis. For continuous time, for discrete time n axis, it always cause a shift towards the right. And for for no tau, delay is going to cause non-zero function value for t less than 0. So for no values of tau, you won't get a non-zero value when t is less than 0. So basically, delay operation is causal, delay operation is not causal. So delay operation is not non-causal, so delay operation is removed from the list. Then we need to check this advance operation. Okay, we need to introduce another slide, I guess. Just a moment. Okay, let us consider advance operation. Advance operation. Advance operation is just the opposite of delay operation. It basically, if you have a signal xt, if you perform a advance operation, it is going to cause xt plus tau, and tau is greater than 0. So let us see its effect on unit step function like before for tau greater than 0. So u of t plus 3, the values we can again write according to the definition is 0 when t plus 3 is less than 0, and 1 when t plus 3 is greater than equal to 0. In other words, we can write it is 0 when t less than minus 3, that is going to be 1 when t greater than equal to minus 3. So basically, the graph of ut plus 3 is shifted to left. It is something like that now. It goes on actually, unit step function t minus 3. So you see, now this function ut plus 3, because of this advance operation, is going to have non-zero values for t negative. That means output is going to depend only on the future versions of the input. Therefore, advance operation is non-causal. But we need to check time reversal also. So So let us move to time reversal in case of ut itself. So it is like time reversal basically means u of minus t. Now from the definition it is like this, and is equal to 1 when minus t is greater than 0. That means it is going to be 0 when t greater than 0, and it is going to be 1 when t less than equal to 0. Therefore we can see, if we plot the for this u of minus t, it's just the mirror image of the plot ut, that is basically like this. If t goes in direction, it is going to be 0 throughout, and it has a value of 1 for all t t negative. So therefore time reversal is also non-causal. So both advance operation and time reversal are non-causal operations. Therefore the correct answer to this question is the fourth option. Okay, let us move to the question when it say xct is equal to cos 3.26t is given as a input to CD converter. Again the sampling period is given as 1/4. So we can write the discrete version as xct sampled at nts, that results into cos 3.26 nts, which is cos 3.26 by 4 n. I am denoting this as cos omega naught n, where omega naught is going to be 3.26 by 4. Now if xn is periodic, in order to xn to be periodic, x n plus n should be x of n. This condition implies cos of omega naught n should equal to cos omega naught n plus some period capital N. Now this condition to hold, this term small omega naught times capital N should be a integer multiple of 2 pi. K is an integer. Therefore we plot the values of omega naught, that is 3.26 by 4 n is equal to 2 pi by k. Now n by k is equal to 8 pi by 3.26. Now you see n is an integer, n and k both are integer. Therefore n by k ratio should be a rational number. But you can see this 8 pi by 3.26 is not a rational number. Why? Because pi is irrational and there is nothing to cancel out this pi. Therefore, we consider first that xn is periodic with n, and then we arrive at a condition that n over k is equal to 8 pi by 3.26 is equal to some irrational number which is not possible. Therefore, xn is not periodic. See, remember how we approach the problem. We first consider that xn is periodic with capital N. If that is true, n over k comes out to be this, which is an irrational number. But by definition, n and k both are integer, so their ratio is always a rational number. Therefore, this condition doesn't hold, or in other words, it is not possible, it is impractical. Therefore, xn is not periodic. So the fourth is the correct answer. Okay, let us move to this 10th question, which is given as xn is equal to sine pi n by 3 plus cos pi n by 7. So let me denote it as sine omega naught sine omega 1 n. Let me correct myself. Let me write this as sine omega 1 n plus cos omega 2 n. Now there are two different frequency components, omega 1 and omega 2. So let me find the period of this signal first. How can we find it? Again, sine omega 1 n, if it is periodic with capital N1, it should be equal to this, that is sine omega 1 n plus omega 1 capital N1. That means this implies omega 1 n1 should be a integer multiple of 2 pi. Now I get n1 is equal to 2 pi k over omega 1. We put the value of omega 1, 2 pi k by pi by 3, cancel out the pi, it becomes 6k. We will take the minimum value of k, that is k is equal to 1, that is our period, so n1 is 6. Similarly, for cos omega 2n, consider it is periodic with period capital N2. So we can write this omega 2 times n plus capital N2. That results into cos omega 2n small n plus omega 2 capital N2. This implies omega 2 capital N2 should be 2 integer multiple of 2 pi, That implies n2 is equal to 2 pi k over omega 2. We put the value of omega 2 in this equation, which is pi by 7. We get 14k. We take the minimum value of k, that is k is equal to 1, to find the fundamental period. So n2 is equal to 14. So let me write the discrete signal again, which is xn sine pi n by 3 plus cos pi n by 7. This is periodic with period 6 separately, and this is periodic with period 14. Now the question is not individual periodicity, but they want the periodicity of xn, which is the combination of both the signal. So the xn is periodic with period LCM of n1 times n2. LCM ensures that a certain period which satisfy for both the sin pi n by 3 and cos n pi by 7 at some multiples of n1 and n2. But it is important for xn to be periodic that this period should satisfy their individual periodicity also. So the period we denote as n, that is period of xn, is LCM of n1 comma n2, which is LCM of 6 and 14. You can see the results come out to be 42, I think. Yeah, 42. So the discrete time signal xn with is periodic with period 42. Okay, so question 11 asks which of the following signals are power signal. So let us first tell you what power signal means. Power signal. Power signal are those signals which has finite power in finite interval. Mathematically we can say limit p of x, power of signal x, is given as limit n tends to infinity 1 over 2n plus 1 summation of squared magnitude of n square, where small n runs from minus n up to n. So this result need to be finite and non-zero to ensure the condition. Okay, so let us pick the first example, which is xn, which is Dirac delta at discrete time delta n. We can represent its power as follows. We say limit capital N tends to infinite 1 over 2n plus 1, n is equal to minus n to n, del n square this case. Now if we see the Dirac delta del n, it has a value of 1 at n is equal to 0, and it has value 0 at all other positions otherwise. So basically among all these del n's, only the Dirac delta at position 0 matters, rest of anyway 0. So it becomes limit n tends to infinity 1 over 2n plus 1 times 1. This is basically 0 because you have 2n plus 1 in denominator where n tends to 0. So not a power signal, not a power signal. Similarly for question 2, where xn is equal to 2 for all n. Okay, let us check whether it's a power signal or not. We put in the mathematical framework limit n tends to infinity 1 over 2n plus 1, where n tends to minus n to capital N. Now xn is equal to 2 for all n, so putting the value of xn here, 2 square, so it basically becomes limit n tends to infinity 1 over 2n plus 1 into 4 times 2n plus 1. Basically at every point its value is squared value is 4, so it's 4 times 2n plus 1, which cancels out, we get a finite power. So therefore xn is equal to 2 is a power signal. So this is correct. Let us move to the third question. I need to introduce a new slide here, sorry about that. Okay, fine. So in the previous we considered, so now it's like a convolution of unit step function. Fine. So third function is xn is equal to convolution of un. Remember, it is not a multiplication, it's a convolution operation, which you can write as from the basic digital signal processing course, u k times u n minus k, a shifted version of it, and you run this over minus infinity to infinity, the summation. So this basically results into n for n greater than equal to 0 and 0 for n less than equal to 0. This is called ramp function. So we'll check it power p of x limit n tends to infinity 1 over 2n plus 1 summation of, in place of xn we'll put n, and the this is negative, this is 0 for all non-negative values. So instead of putting small n from minus n, we'll start from 0 up to capital N square. The results comes out to be limit n tends to infinity 1 over 2n plus 1 we can write it as n is equal to 1 up to capital N or n square. The formula can be written as n times n plus 1 times 2n plus 1 by 6 over 2n plus 1. So it turns out to be infinity. Therefore, not a power signal. Third option is also not a power signal. Fourth option we will next check. Fourth option is xn is equal to n mu n, which is basically the same as previous, n for n greater than equal to 0 and 0 otherwise, ramp function. Therefore it is also not power signal according to previous calculation. So this is also cancelled out. So only the second signal is power signal. Okay, let us move to the concept of energy signal. Energy signal are those basically containing finite energy. Finite energy, and mathematically we limit n tends to infinity summation from small n from minus n to n squared magnitude summation need to be finite. Condition for energy signal: non-zero and finite. Yeah. So for first signal, which is xn, is equal to summation of k from 0 up to 2024 Dirac delta at these positions. Let us check the energy of the function. We write limit n tends to infinity summation small n runs from minus n to n Dirac delta n minus k is equal to 0 to 2024 square. So basically this function is 1 when n is equal to k and 0 otherwise. So you can see limit n tends to infinity summation runs from minus n to n. Another summation over k is equal to 0 to 2024. You are running this summation. The answer basically comes out to be 2025. It's a finite number, so xn is energy signal. Correct. Second question, the second signal xn is equal to 2 for all n. Therefore, its energy is limit n tends to infinity. Small n runs from minus capital N to n to square. This results into 4 times 2n plus 1, and limit n tends to infinity. So it is not finite. Therefore, the second signal is not a energy signal. Now we'll move to the third signal. We need to introduce this slide. Just a moment. Yeah, thanks for maintaining the patience. Now third signal is again from our previous discussion. We can see our third signal xn is equal to convolution of unit step function with itself, which is a ramp function, which is n for n greater than equal to 0 and 0 for n less than equal to 0. Therefore, energy of this function comes out to be limit n tends to infinity, summation over small n runs from minus n to capital N, xn whole square, limit n tends to infinity, small n running from 1 up to capital N, n square. It results into capital N times capital N plus 1 times 2n plus 1 over 6 when n tends to infinity. Therefore, the result is not finite, for this function is not an energy signal. Similarly, the fourth signal given as n un is just same as 3, which we have already shown that not an energy signal. Therefore, see, only one is energy signal, rest of them are not energy signal. Okay, you have a discrete time system. Your input is xn, your output is yn. such that it is x square of n non-linear system. Now xc is band limited to 250 pi radian per second. That means if I plot the spectrum of xc of j omega, its maximum frequency component lies here, radian per second. So what is the largest sampling period Ts such that yct is equal to xc square t? So you see, largest Ts is nothing but smallest Fs, where Fs is sampling frequency. Now when you square a system like this, discrete time system is a nonlinear system which input output relation is given as this x square n. This square operation sometimes introduce harmonics. That means if maximum frequency of x n is f, max frequency of x square n will be 2f at certain times. So we have to ensure the sampling period, sampling is done at such a rate such that we can get the yct as xc square t. The recovered continuous reconstructed signal yct, that is reconstructed from yn, is equal to square of the underlying continuous time signal xct. So basically you have to consider, if xc is band limited to, now okay, let me just show here. Multiplication in time domain results into convolution in frequency domain. That is, in frequency domain it becomes this, and the sign is convolution, and this convolution operation results into maximum frequency component to be 2 times 250 pi, that is 500 pi radian per second. So you have to ensure the sampling rate, sampling frequency, such that it preserves, such that you are enabled to reconstruct the signal without any distortion. Therefore you should sample at a rate twice than that 500 pi over 2 pi rate, that is 2 times 250, which is 500. You have to sample the signal at 500 Hz to ensure that the nonlinear output yn you are getting when you are reconstructing it, the underlying continuous time version YCT is the undistorted squared version of the continuous time signal XCT. So for that, this sampling frequency Fs is 500 is at least required. That means your largest value of Ts can be Ts is equal to 1 over 500. That is the maximum sampling period or sampling duration you can afford. Second one is the answer. Okay, with this I finish the problem solving session. If you have any questions, you can ask me out. Bharat, thanks really for being with me all this time. I messed up in some questions, I know, but you are still there, you are still listening. Thanks for that. So
Thank you.
any part you need clarifications on or something I could help you with, just say if you.
Will this video be uploaded on NPTEL portal or
Yes, it will be uploaded. It will be uploaded in my personal YouTube channel. I think you will get the link also from that. I think this instruction sheet, like some link is you are uh, getting, right? Or like this video will be uploaded in YouTube from my personal channel, and I think you will receive the link also.
okay, thank you.
Okay, okay, okay. Thank you, Bharat. So if you have no question, I am ending this meeting.